Okay, let's get started. Good morning, good afternoon, good evening. Thank you very much for joining today's tinyML talk. I am Wei Xiao from ARM. I will be your moderator for today's session. Huge thanks goes to our tinyML talk sponsors, DeepLight, Kixel, Edge Impulse, Reality AI, Maximum Integrated, and SyncSense. We have additional sponsorship slots available. If you're interested in make this program possible, please email betty@tinyml.org. Let's watch a short video from our sponsor, Kixel.
Kixel AutoML is an intuitive end-to-end machine learning platform that automates labor-intensive tasks. Data from user-selected sensors can be collected and labeled in real time or uploaded from an existing data store. Features are automatically extracted from the data and weighted based on importance. Kixel AutoML offers a wide variety of machine learning algorithms, including regressors, decision trees, and neural networks. A selected model is deployed for live testing with one simple click.
Let's take a look of our next tinyML talk agenda. On Tuesday, September 1st at 8 a.m. Pacific time, we will have a presenter, Suri Chirasaria from Arizona State University to talk about how adaptive video subsampling can be applied to energy efficient object tracking. Christopher Carlson from BrainChip will introduce the Akida neural processor. If you want to present in our series, please email your proposal to talks@tinyml.org. So let's move on to today's presentation. The recording of today's session will be posted to tinyML YouTube channel by tomorrow. If you have any questions during our presentation, please use the Q&A window to raise your questions. Our first speaker today is Mark Stubbs from Shoreline IoT. His topic is practical application of tinyML in battery-powered anomaly sensors for predictive maintenance of industrial assets. Mark is the CTO and co-founder of Shoreline IoT, leading a team to revolutionize data gathering and predictive maintenance in industrial applications. Mark also held positions at Google, Agilent, and Apple before he co-founded Shoreline IoT. Mark, welcome, and please take over.
Thank you, Wei. So what we're going to be discussing today is a real-world application of tinyML that addresses some of the key issues in industrial IoT monitoring, in particular sensors with that are very low power and have very long battery life. So we're going to talk about the use cases, why tinyML is important, and that includes the long battery life, the low power wireless, and then how you build and deploy the tinyML model for these applications. So the use cases that we have in industrial IoT are to monitor lots of various machines and processes in the industry. These include monitoring the bearings as they wear out, shaft misalignment, noise from the bushings in the bearings, looking at prolonged moisture exposure in certain environments. Moisture is very important to monitor. Pressure loss, flow variance, over temperature, and many other applications. So what we've developed is a peel and stick sensor that has tinyML embedded, then combined with our cloud proprietary software allows us to provide an end-to-end solution for CBM, PDM, and APM. So condition-based maintenance, predictive maintenance, etc. So the problem out there today is a lot of the maintenance is reactive. So they will identify that a machine has gone down, there's a problem, somebody comes out, they visit the site, they find out they need some additional parts, they have to go back and get it. So what we're trying to do is improve that flow. We're trying to catch things before they go completely wrong. Current solutions are slow, manual, and labor intensive, and a lot of the data gathering is a little bit difficult, especially with COVID right now. And the analysis of a lot of the data is done by experts. So what we're trying to do is build a platform that gets a lot of that knowledge in place so that you can have that analysis done and at your fingertips. There are many new Industry 4.0 solutions. The problem is these have slow adoption, they're too expensive, they're not very easy to use, they're still labor and time intensive, and they have battery life limitations. So why 5-year battery life is important? So the old method was walking around with data collection. So if you're doing something like vibration monitoring, which is shown here, you would actually schedule a route where you would go around and you would monitor the machines either once a week or once a month. The problem with this is not only the manual probing of all the machines, which is very labor intensive, but there's also the issue that you could be missing things that are happening in between. So you want to get that insight into your machines. Are the current IoT solutions attempt to solve this? But in their attempts, they are still about 3 months battery life, typically. So that's the problem. So we wanted to come up with something that allowed you to install anywhere without power, no cables needed, and continuous monitoring. So this is where tinyML comes in. It helps us monitor the assets continuously and find those conditions that would normally be missed. So our sensor is very efficient, highly scalable, long battery life, allows you to continuously monitor. And what you see highlighted here on all these different machines in different locations are where the sensor will be mounted to pick up the information and send it directly to the cloud. It's very straightforward to set up, has long battery life, and provides continuous monitoring of these assets and only alerts you when something goes wrong. So in many of the applications that we're looking at, the requirements are there's no power available. These machines have often 480 volts, very high voltage. So to connect into that is very impractical and very expensive. So it's important to have a peel and stick battery operated sensor that can just be installed in that area very quickly. And it's also there to detect and reduce downtime. So we need to collect lots of data, upload very little. So this is where tinyML helps us. The model that's running at the edge in the inference engine is able to sort out all that data and find what we call the needle in the haystack. So this little bit of useful information is filtered out from all of the other information that's constantly going through the machine. So we can find that event or that problem that's happening in the machine, and we can send that up to the cloud so that the user is aware that there's a problem. So current solutions, there's no historical, or in order for our solution to work, we don't need historical data. You don't need machine learning know-how, and you don't need experts or training. So it's very easy to use and set up. The device will learn what's normal when you install it. You tell it your machine is operating normally, and then it's up and running and ready to go after a short training interval. So no gateway, no wires, wireless IoT, low power wireless, all very important in making this solution practical. So a few details about our neural network. So we are using Google's TensorFlow Lite for microcontrollers as our inference engine at the edge. And we have a small few hundred parameter model that's actually operating in an ARM Cortex-M4 from AMBIC. So this MCU is able to continuously monitor. We're monitoring about every 10 seconds to look and see what's going on with the machine. Depends on the frequency that the user specifies, but that's the fastest we can currently monitor. The inference engine operates when looking at the accelerometer for vibration waveforms. We're looking at the raw accelerometer waveforms. And what we're doing is we are looking at that raw time domain and we're trying to predict what's going to happen with it. So our model is actually analyzing and looking at that waveform that says, what's the next step? Does the next step look like I predicted? If it doesn't look like it predicted, then that's a potential anomaly. Once you get enough of those to cross the threshold, then it sends the alert. So it compares those predictions to actual sensor readings, and then that's how it detects the anomalies. And then it sends that up to the cloud. So at this point, we can run the demo. I see I'm running a little bit fast, which is good or bad. So a little bit about the demonstration that we have. So we have this motor with an offset weight. So this basically simulates a load imbalance. So there's a problem with the load that's attached to this machine. And if we run it at low speeds, then you're not going to have any problem. On top of it is our sensor. The sensor is mounted on the bearing housing to pick up very good signal from the machine. So we can pick up bearing issues, load issues, etc. in this particular machine. We're also controlling it remotely using our technology. We have another of our products over here that controls the variable frequency drive from the motor. So I'll just crank that up now. I've got it set for about 600 RPM. So I'll click that up. And there's a little bit of delay. So while we're waiting on that to start, let me switch over here. So on this screen, what you're going to see is all of the data that's coming in. So we have 3 channels of accelerometer data that comes in, the X, Y, and the Z, and we can actually explore and look at that data once it loads. Quick to see, yeah, now the motor is spinning. So we've got the motor spinning at about 600 RPM. You can see everything is normal, and you've got all the access to historical information, cellular signal strength, etc. So now what we're going to do is we're going to go in here and we're going to crank the motor up. So now things should get a little bit more interesting on the video once the motor cranks up to full speed. All right, we're up to full speed now. I see my wires vibrating a little bit. So we're getting some good vibration there. And we should see, so the red light, I believe, has come on. It's hard to see in the video. And then once the cloud syncs up, we should get the anomaly here. So in theory, it can take about a minute. Because right now it's on a 1-minute cycle as it goes around. I can definitely see I've got some good vibration there. There we go. So I'm not getting the indicator here, but I do have the text message here on my mobile device. So I did receive the anomaly here. So I know it came in. There it is. So there we go. So what we've done is we've detected that that problem is present at the edge. Now we can shut everything off. Okay, let me go back into the presentation. So what you've seen there, just to review really quickly, is the sensor mounted on the motor, and it's had a model that's been trained and deployed. This model detected when those vibrations went out of spec, when it became abnormal. It then sent the information up to the cloud. Then it sent the notification to my mobile device and also set the indicator on the cloud. At that point, we can launch a workflow that issues a ticket and a work order to go repair the machine and take action. So the other important part of this is auto-scaling the back end. So we're using SageMaker and EC2. And what we do is we learn what normal is for that particular machine. For scalability, one of the big problems out there is every machine has its own unique signature. So what we have to do is learn that machine's signature, and then we have to train our sensor so that it understands exactly what we're looking for. So we monitor what normal operation is on that machine for a period of time told to us by our user. And then we go to the back end, we take the data that we've captured, we scale and train the model, and we send it back down to the edge. And at that point, it's running and it's looking for that needle in the haystack. And then that's how we get the 5-year battery life. So that's how the tinyML comes in. That's why it's important, is because it allows us to find that information. So instead of just sending all those data logs up to the cloud, we're able to go through, find the useful and interesting information, send it up to the cloud, and let the users know that there's a problem that needs to be addressed immediately. And we also have flexible model development workflows. So you can either have data that's coming. So if you have a company that's got a very rich data set, they've collected a lot of history with their vibration analysis tools, they can bring that data and a model can be built for them. Otherwise, our live data can be used to train and understand. So you have the option of either going from your historical data and having a model built for you off that trained data set and deployed to the sensor, or you have the option of learning based on the machine operating normally today. So we have a Shoreline device agent, and that's executing the inference engine when it's available. And that's how we actually do the whole training workflow. So the agent comes up, we tell it record for X amount of time, it sends its information, all the data logs up to the cloud. And then once it has recorded enough data per the requirement, we then train and deploy the model. So that model is then sent down and that agent applies that OTA for just specifically the model portion, and then it starts executing and running. Okay, that's it. So are there any questions? Wei, you're on mute. Hey, Wei, you're muted.
Apologize for that. Yeah, we received a couple of questions from our audience, so let's try to address them one by one. Our first question, you train the models in the cloud and deploy it at the edge. Is that right?
That's correct.
How often do you train the models?
So it depends on the requirements. So we have a continuous training. So what we're doing is we are continuously background monitoring the asset, and we get feedback from our customer. So if the model, when you get the alert, if it is a false alarm, then the user specifies that. So when the alarm comes in, we get the alarm as well as we get the data. And then that gives us the option to tag that data. So the alarm by default tags it as an anomaly. And what we do, if the user says, no, things are actually operating within spec still, then we tag that. Once we have enough of that, we retrain and redeploy. So we can retrain and redeploy every time that occurs, but we are continuously monitoring, and we're looking on sort of a weekly, bi-weekly basis. We're looking at redeploying the model as necessary to adapt with the instrument. And there will be some trending over time, so we are monitoring the trending of the asset using some other techniques.
Thank you, Mark. The other question, so how do you trigger an anomaly?
So the anomaly is triggered, are you talking about in the demo, or just how do we trigger one with the, in general?
In general,
yeah. So in general, I mean, we don't trigger one, the machine does. So the machine tells us when we need a problem or it needs help. So machines have many different failure modes, whether it's roller bearings or broken gear teeth or whatever, that each machine has a signature. And that signature is very clear to the model. So what happens is it learns what the normal state of the machine is, and it can kind of pick apart those vibrations and understand this is what things look like normally. So let's say on a gear mesh, if the gear mesh breaks a tooth, then what's going to happen is it can very clearly pick up that signature from the machine, and that triggers the anomaly. So that at the edge is how we identify that there's a problem. It sees that difference between normal behavior and this new abnormal behavior. And then it sends up that signature as well as the anomaly trigger, and then we send the alerts out from the cloud.
Thank you. The other question from our audience, can you explain why you are looking at raw acceleration data rather than something like an FFT to feed to the NN model? The raw acceleration data seems to be vulnerable to different positions of the accelerator, accelerometer.
Correct. Yeah. So we manage that a couple of different ways. So we have both options. So if somebody comes to us and the vibration data that they've taken is based on FFT, so they look at the spectrum to determine their signature, and that's how they've trained, then their model can be deployed with an FFT. The reason we chose to do it this way is because it saves us the time of doing the FFT on the end device, and we are also controlling the way that the physical sensor is mounted. So there's an alignment post and there's a pad that physically goes onto the machine. So the sensor is actually mounted in a known orientation on the machine, and the training is done in that position. So when you're using our onboard training, it actually is picking up that machine from that position. So the machine is rigid mounted, and it should have a fairly consistent signature once we're mounted. So hopefully that answers that.
Thanks. Next question, what's the low power wireless communication protocol you used in this demo?
Right, so we're using cellular for this particular application. So we're using CAT-M1 and MB1.
Thank you, but you network as well, right? And other protocols.
Right, we can support other different protocols as well. But yeah, it doesn't have to be this particular wireless protocol.
Okay. So next question, what machine learning approach to detect anomalies are you or unsupervised learning models?
Missed part of the question, but I think you asked what techniques are you using to do unsupervised models?
Are you using time series models or unsupervised learning models?
Yes. So yeah, it's a little bit of both. So it's a predictive model, so it is looking at the time series, and it's actually trying to infer from what's happened what will happen. So what we're doing is we're actually projecting, and then we take those measurements and we compare the projection. And when we see divergence beyond a certain amount, that's when we trigger for the unsupervised case.
Okay, so next question. Have you based knowledge, for example, physics-based modeling to capture physics of the machine to be monitored when the models are trained?
Yeah, so we're not using physics to capture at this point. So everything is very diverse, and the reason we don't do that is because it's a configuration issue. It's difficult for us to have the end customer say, here's what the machine looks like, here it's mounted. There's lots of variables, so it's very challenging to capture the physics, accurately. So that's why we try and take a little bit of a data log to understand what the machine is doing, to do it empirically rather than kind of calculate it. We do capture enough of the configuration of the machine that we know some of the parameters for that machine, like we know what its default running speed is, we know what the gear ratios are. So based on that, belt ratios, everything else in the machine, we can at least set up kind of a standard operating parameter set. So we do have some knowledge of the machine that's baked in.
Okay, so what's the sensor used in this demo? And probably in general, what sensor types do you support?
So our sensor type used for this particular demo is a triaxial accelerometer. So it goes up to 64G, and it goes up to 25.6 kilohertz on the ODR. So it allows us to do up to about 10 kilohertz. It does have a bandwidth of around 8 kilohertz in the analog section. So that allows us to do a couple of different things, from monitoring the running speed of the machines down their RPM. So the RPMs of these machines are typically 1800, 3600 RPM. And then you're also able to pick up the higher frequency stuff, which is in the bearings and the other noise. So that's the accelerometer, and it's used for those sorts of vibration applications and picking up those signals. We have microphones which go up to 40 kilohertz. So that allows us to pick up ultrasonics and other sounds in the factory floor to listen for those anomalies. We have temperature and humidity. It's one of the early things I mentioned. Temperature and humidity in certain processes are extremely important to monitor because that can affect the outcome of that particular process. Plastic injection molding comes to mind as one where the humidity in the environment has an impact on the quality of the part produced during that process. We also have an external input that allows us to monitor a variety of analog sensors. There's an industry standard 0 to 10 or 4 to 20 milliamp input that allows us to monitor energy, so current, voltage, flow, level. So if you're on a tank, you may want to monitor the tank level. You can monitor pressure. And with that, you can have multi-parameter monitoring where you're looking at the machine. So you're understanding what the machine's output is, as well as how the machine is operating. So we have a combined set of sensors in the device itself that allows us to kind of pick up what's going on in the machine.
Okay, so our next question, I think you already addressed this partially. I understand how this works with detecting bearing vibration problem. What other applications can you use this technique with? Mark, anything else you want to add here?
So let me go back to the slide that we had here. So we had the bearings, we had shaft misalignment. I mentioned the gears. So gear meshes, you can detect when there's a chipped or broken tooth in a gear mesh. The prolonged moisture exposure, so that one's fairly simple. Pressure loss, flow variance. So with the anomaly detection, you're looking at lubrication, you're looking at the bearings, you're looking at cracked rotor bars in the motors themselves. There's lots of things that you're trying to look through everything, machine looseness. So there could be other problems in the machine where something gets loose, or you've got some load or something is sticking in the machine that's not supposed to be there. So we can start detecting all these different signatures in these complex machines. So the idea is we're actually putting multiple ones of these sensors on and creating sort of a virtual machine in the cloud that knows how this entire system should be operating. And we're taking all that data to understand that that machine is operating as it should be normally.
Thanks. So next question, how can one distinguish between gray zone and black zone? So for those who are not from industrial background, including myself, wet zone refers to machine operating at 100% accuracy. Black zone is 100% fatal machine operation. Gray zone is the transition area in between.
Yeah. So that's where monitoring the output of the machine, monitoring the OEE, the operating efficiency, that's where it's very important to kind of monitor the entire process. So you can kind of pick up from the machine that it's got some vibration issue. That's not necessarily going to cause the machine to lose its operating efficiency, but if the problem goes unchecked, then eventually the machine could break and have a catastrophic shutdown. So you want to make sure you can do scheduled maintenance there. I'm not sure if I'm answering the question very well, but you're basically trying to operate or measure and monitor all these machine operating parameters. And that's building your model of the machine in the cloud. So you know kind of what your ideal operating conditions are for that machine. And you're trying to understand that everything is within those ideal operating conditions so that you're getting the expected output from that machine. So it's pulling all that data in from all those sensors, and then kind of building that virtual machine to see that your model of the machine and your actual machine are in sync.
Thank you. Next question, can the sensor train update its own model over time to accommodate machine aging?
Yes, so we are doing that, we're trending, and as the machine ages, we try not to let it. So there's the classic problem that I'm sure people have seen in machine learning where your Nest thermostat learns a crazy pattern and it's not the pattern you'd like your Nest thermostat to operate on. We don't want the machine to adapt to everything that's going on because eventually it will adapt to failure. So we are adapting slowly, but we're also taking user feedback. So if we get false anomalies, then we take that user information and say that no, the machine is still operating normally. So we're trying to capture information from our users to understand what's normal for that machine. Try not to bug the user too much, but try and have enough threshold on there that we're not going to overwhelm the user with alarms and false anomalies.
Okay, so our next question, how suspectable is the anomaly detector to external vibration coming from neighboring machines or other load changes?
So it should not be, there is susceptibility there, of course. Many of these machines are mounted on concrete floors, which are going to transmit the vibration from nearby processes and nearby machines. During the training process, we're trying to learn all the different normals. So if the manufacturing floor operates in a normal way, meaning every shift you kind of run all the different machines in a typical way, we try and learn that. So we are monitoring that. The reason we are so tightly coupled to that machine's bearing housing is that signal is our primary signal. Everything else is kind of secondary background signals. So we are looking at those primary signals. We can actually set a floor on it as well if we start picking up too much extraneous information. So if we want to kind of filter out a lot of the additional factory noise that's coming in, but we will learn some of that factory noise as normal. So that's one way that we work around that susceptibility in our deployments.
Thank you. Yeah, in observation of our time, we will probably wrap up here. So for the unaddressed questions, we will answer them on tinyML forum. Before you go, Mark, last question. If somebody is interested in test driving your solution, who should they contact?
They should contact me at Shoreline IoT. So my contact information, I believe, will be available on the slide deck, and I believe it's in the presentation. If not, you can also find me on LinkedIn.
Thank you. Thank you very much, Mark, for presenting.
All right, thank you, Wei.
Yeah, thank you. So big thank you goes to our tinyML talk sponsors, DeepLight, Kixel, Edge Impulse, Reality AI, Maximum Integrated, and ThinkSense. Again, if you are interested in sponsoring our program, please email betty@tinyml.org. So DeepLight provides an AI-driven optimizer to make a deep neural network faster, smaller, and energy efficient. Edge Impulse offers online tinyML lifecycle solutions, which transform developers' abilities to deploy machine learning to embedded devices. Maximum Integrated enable edge intelligence with their sensors and signal conditioning technologies. Advanced AI acceleration solution is coming soon. Kixel's AutoML platform builds tinyML solution for the edge using different sensor data. Reality AI offers optimized feature discovering, compact embedded code, and optimization toolkit. They also provide tools for managing the cost of data collection. ThinkSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. Again, please join us on September 1st, Tuesday at 8 a.m. Pacific time to learn from our speakers from Arizona State University and BrainChip. If you have other proposals for our tinyML talk sessions, please email your proposals to talks@tinyml.org. Thank you for your participation.